study of lunar tidal evolution. And the second half is some of the new results that deal with the dynamics of lunar core, which is quite relevant to the talk we had earlier today by Ian. So evolution of Earth-Moon system, or our understanding of the evolution of Earth-Moon system, can be compared to the video formats, okay? So for younger people, say Simon, this is a VHS tape. And this one, I don't know what this is, but it is apparently Betamax. So in the 80s, everybody was saying, who knew those things, that Betamax are better, but VHS won. So technology is contingent upon historical development. So I'm going to make a case that our understanding of like what is canonical giant impact and what is modified is a historical accident, which has to do with how the theories evolved over time. Okay, so the history starts with Goldrake. I think we established that well enough so far. So there is the famous 1966 paper by Peter Goldrake, which tried to like play the tape back on the tidal evolution of the moon. So the basic idea is that the moon's orbit grows as the tides on Earth, raised by the moon, dissipate energy. The rotation of Earth slows down over time, while the orbit of the moon grows. And this is an ongoing process. And the idea is that if you do the calculations right, you can figure out what kind of orbit did the moon start its tidal evolution, which will tell you something about the process by which the moon formed. And these are kind of canonic, well, the iconic plots, which are a bit hard to read. So this is, for example, the inclination of the moon relative to the ecliptic, the Earth's orbit around the sun. So now we are here at 60 radii. So all of these plots do not have time explicit, but they are plotted as different quantities are plotted relative to the distance of moon from Earth. And time goes this way, but really we only know the point at 60 Earth radii, where we are now. And calculation more or less goes backwards in time, although technically it can go either way depending on what we're doing. So right now the inclination of lunar orbit to ecliptic is about 5 degrees. As we go backwards in time, it grows slightly, and then it becomes this thick line. I mean, this should all be black, basically. It's just that they didn't want to print it all that ink. So basically oscillates between these two extreme values, and the reason for that is that early on, Earth and the moon, Earth's spin axis and the moon were rapidly precessing around one another. So, for example, the obliquity of Earth, so now it's 20-something degrees. To go back, it also oscillates because the moon and the Earth's axis are oscillating around each other. But what gets thinner is the inclination of lunar orbit to the equator, because right now it oscillates between extreme values depending which way Earth's spin axis is pointing and which way the node of lunar orbit. But when you go back in time, the proper plane relative to which one should measure inclination is the equator of Earth, and that inclination is 10 degrees or a little bit more, or like a few, like say 5 radii from Earth. So well, Goldrake played back the tape and found that the moon formed at 10 degrees inclined orbit. And that's bad. It shouldn't be happening, because if the moon formed from a flat disk, you should have 0 inclination. So that's the beginning of the inclination problem. Then, chronologically, came a paper by Bill Ward about the evolution of lunar spin axis. Now, this is one of the ugliest plots ever. So I'll explain why this plot is so ugly. So the orbit of any kind of Keplerian orbit has 2 kinds of precession. One is usually in the direction of orbital motion, where the long axis is moving in the direction of orbital motion, which here is counterclockwise, in the plane of the orbit. It's just that the long axis is rotating in space slowly. The other kind of precession is that the line of nodes, the intersection of the orbit to the plane, which we call Laplace plane, which is the plane of the outside perturbation. Let's say, in this case, orbit around the sun. And this is a satellite orbit around the planet. So the line of nodes, which is the intersection between the orbit and the reference plane, moves usually opposite direction of orbital motion, here clockwise. And so there are two kinds of precession: precession of the line of apsides and the precession of the nodes. And the plane that determines, or around which the plane of the orbit precesses, is called the Laplace plane. It actually is the definition of Laplace plane, more or less. So how do we define this plane? Well, far away from the planet, it's the plane of the orbit around the sun. Why? Because the sun is perturber, and the solar perturbations are symmetric around the ecliptic, so that will be the Laplace plane. Close to the planet, if it's flattened, like shown here, it will be the plane of the equator. So if you're orbiting close to the planet, like artificial satellites do around Earth, their orbits precess around the equator of Earth. The moon's orbit, which is far out now, precesses around the ecliptic, the Earth's orbit around the sun, because the sun is the main perturber, as opposed to the equatorial bulge close in. And there is a smooth transition between the two, which looks much nicer in real life than what I've drawn here. So that's the concept of Laplace plane. And then when you realize that the orbit precesses around the Laplace plane, you add on top of that the fact that the spin axis of the moon also precesses around the orbit. So you have one precession on top of the other. And that's very complicated. So in nature, the real moon wants to find the lowest energy state. And those are called Cassini states. And there are different kinds of Cassini states depending on which dynamical regime we operate in. So if the natural precession, rate of the precession of the spin axis is faster than that of the orbit, then the spin can precess around the orbit while orbit is barely moving. So then the spin stays close to the orbit normal. That's the red here. Actually, this angle is usually very small. And that's for example, that's how all the satellites of Jupiter and Saturn are, more or less. That their spin axes are very close to their orbit normals, because the spin is precessing rapidly around orbit normal, which then is precessing around the Laplace plane normal, which is the blue. But right now, the moon actually has a slower precession of the spin axis than the orbit. And the reason is that moon is far from Earth. Its spin is precessing because of torque of Earth on the shape of the moon, which is weak because moon is far from Earth. But the orbit is precessing because the sun is tugging on an orbit, which is fast, because the sun is a strong perturber. Further away the moon is from Earth, stronger the solar perturbations. In that case, the spin axis cannot follow, the spin axis here, black, cannot follow the orbit normal, but kind of stays close to the Laplace plane normal. So as orbit normal is precessing around, the spin axis stays close to the Laplace plane normal, which is the ecliptic in this case. And the Laplace state dictates that these three are in the same plane. So what I've drawn in the plane of the slide is actually naturally the plane in which all three vectors are. So the only interesting catch is that as the moon is moving away from Earth, first, this Cassini state 1 is stable, but then at some point, the second Cassini state becomes stable. So this plot in Bill Ward's paper is drawn in that plane that contains all three vectors. They've only been spread out along the y-axis. So first, the spin axis is close to the orbit normal, which is the red vector is basically this line. But then it has to switch to being close to the blue line, that is the ecliptic normal. But it cannot go in between, it has to approach from the other side. So it diverges, jumps to the other side, and comes back to being close to the ecliptic normal. And during this transition, which is more or less a resonance between the precession of the axis and the orbit, you can have large obliquities of the moon. That means that the moon has a large tilt to its orbit around the Earth. The moon's spin axis has a large tilt. And this is forced obliquity, which means that it cannot be damped because it's forced by the inclination. So to damp the obliquity, you need to damp the orbital inclination itself, which we'll come to. Okay, so then there was this paper chronologically, next came the paper in 1978 by Peel and Casson, where they were looking at the tidal dissipation within the moon because of this obliquity, because there are these things called obliquity tides. As the obliquity is large to one side, the bulge is going to move from the northern hemisphere to the southern hemisphere on the near side and the opposite on the far side. So you can see that the tidal deformation of the moon, because of obliquity as the moon goes around the Earth, is going to make the nodding of make the moon nod and the bulge go up and down, north-south, which is equivalent to librational tides with eccentricity. And this generates heat because the inelastic body is being constantly squeezed in different directions. So because this transition happens at 30-something Earth radii, when moon is pretty far from Earth and their evolution is relatively slow, the power is not very high. So you can see that the power of tidal heating, well, maybe this is the best one. It goes down, then goes up for a while, but never reaches the level of radiogenic heating, and then goes back down. So Peel and Carson decided that there won't be much heat coming from obliquity, so we can forget about it. The only problem is that they haven't considered where is this energy coming from. Even if this heat is not affecting the surface of the moon more than the radiogenic heating, it's still a large amount of energy that has to come from somewhere. And that somewhere is the orbit, but it wasn't considered. So the evolution of spin axis and the evolution of the orbit of the moon were considered by different people using, like in different literatures almost. Okay, so we come to two-man wisdom, which is kind of the beginning of the modern age, because it's the first numerical study of the orbital evolution of the moon, and it has both semi-analytical and a purely numerical model, which agree, and both agree with Goldreich. So it's shown that Goldreich's approximations were correct. And under those assumptions, when you play the tidal evolution back, you get 10 degrees or more early inclination. But once again, the limitation is that the evolution of lunar obliquity wasn't taken into account, which can change the picture. Interesting thing is that literature on outer solar system satellites, including Triton, had obliquity tides at this point, but somehow just never got into the lunar tidal evolution until later. Okay, so then comes my paper about losing angular momentum through the evacuation resonance. I skipped two-man wisdom 98, which introduced the evacuation resonance, which I here use to lose angular momentum. So I won't talk much about this because I think Jack is going to talk more about the evacuation resonance. But for the main purpose of my talk, which is that we were missing this obliquity tides from the picture, this paper did not advance the field at all. Because yes, we were looking into lunar formation with high angular momentum, but really we were still doing the tidal evolution without fully understanding the evolution of obliquity and inclination. And this is interesting. This was the last plot of the talk I gave just around the time the paper came out. And so this is evacuation resonance with zero inclination. So it doesn't change inclination, then we run into so-called eviction. I won't talk much about it. It's yesterday Jack talked about both eviction and evacuation. So so basically, it doesn't evacuation resonance doesn't induce inclination, but you have to then play with eviction, possibly the same way as two-man wisdom 98. Also, while you're using angular momentum, you're losing a bit of inclination, but you can also imagine that through the Ward and Canup model, you create an inclination before you go to the evacuation resonance. So what I was saying, well, we don't really solve the problem. Maybe what people were proposing works, but it's kind of, I didn't really think, like something is missing here. Like if we solve the problem correctly, this problem with inclination should naturally be solved. And what we're doing here is we are trying to stretch existing models to accommodate this new twist. So what it really got, finally, like the dots were connected that the tidal evolution should include obliquity tides, was work by Irina Chen starting in 2013, and the paper was finally published in 2016. So this was the LPSC abstract by Francis Nemo from 2014. Important thing is that they model obliquity here, and they show that the inclination of the moon, depending on what properties of the moon you use, can drop during high obliquity phase. Because it's a forced obliquity, obliquity tides try to shrink obliquity, but because it's forced by inclination, what gets shrunk in the end slowly is inclination. Here, they overestimated, I think, damping of inclination because they used a special model of magma ocean, but that's not so important. The important part is that this is the first time the inclination and obliquity tides were properly taken into account. So that kind of inspired my Nature paper in 2016, where I did a numerical model of the Cassini state transition for a solid moon. And I find that it's actually very interesting. If you go back in time, the moon had inclination of about 30 degrees at some point, which dropped a lot during Cassini state transition. And we even had a non-synchronous rotation at this point. I'll come back to that because there's more twist to this. But basically, if moon had high obliquity and obliquity tides, that means that inclination might have been much higher in the past. So that 10 degrees, that was our problem to begin with Goldrake, became 30 degrees. Now, so small fixes are not going to do it. So what I proposed in that paper was the Laplace plane transition between high obliquity Earth and the Sun. So I just already showed this plot that, so Laplace plane, as I said, is the plane around which the nodes of the orbit precess. And if it's a low obliquity planet, it's continuous between the equator and the ecliptic. But what if it's a high obliquity planet? It's not clear how it connects, because at some point, should it be retrograde or prograde? Well, there is this discontinuity in which if the satellites that orbits at that distance, its orbit is somewhat chaotic. That the circular orbit becomes eccentric, and that can induce damping and loss of angular momentum, which is what we proposed in 2016 paper, that the moon evolved out and got to about 18 Earth radii, and then got stuck for a while, which during that time it lost angular momentum. It's a complex thing that Jack is also going to talk about later, so I'm not going to spend much time here, but this is a major reworking of the whole picture that requires early Earth to have high obliquity, and it comes as a natural consequence of obliquity tides. This is a movie that, this is a pretty ugly movie which won't play, so that's good. So I'll skip this. We ran different initial conditions. The most important thing is, depending on which obliquity you choose, you end up with different end states and angular momentum in the end. So you can either drop into Earth, or you can lose a little bit of angular momentum, or just the right amount. And that's determined by the original obliquity of Earth. This discontinuity works for obliquities over 60-something degrees. If obliquity is smaller than that, there is a continuous evolution. So this is the first half of the talk. So it's a difficult problem, and it really, like, the lunar tidal evolution is what constrains the giant impact. Without our understanding lunar tidal evolution, there would be no idea of giant impact. But really, how we define classical or canonical giant impact has to do with the original setup of the models of tidal evolution. And if some of the papers are shown were published in a different order, if Ward's paper came out before Goldrake's, it's very possible that our idea of canonical giant impact will be very different from what it turned out to be. So there are, to some extent, historical accidents that the canonical giant impact might not be the best, might be just the VHS tape, which won, but although people say it wasn't as good. But no reason not to use DVDs or digital or whatever. The main thing that was ignored for a long time is the obliquity tides and damping of inclination. So that's the first half of my talk, which is, as you see, a rant. So I'll take questions for this now, because it's going to get very different in the second half.
Okay. Thank you for this talk. Are any questions?
Well, I'm far off from this field, so I'm like a total stranger. But still I have yet a very rudimentary question. Like when you go into the analysis of the motion and the various features as characteristics of the lunar movement, do you just simply observe these facts, observe them and calculate and reach mathematical results and physical results, or would you consider the functions of these further in depth? Does it lead you anywhere to a grand designer of this, like the concept of God, or you don't bother at all, or it leads you away from God?
It's a philosophical question. So far, it looks like giant impacts just happen by themselves, and so far there is no. Well, let's say the science is philosophically, is pragmatically naturalist. Like the assumptions we take are assumed that these are natural processes. So we cannot reach any conclusions outside of that.
Are you going to talk about the difficult issue of tidal parameters? What I'm getting at, of course, is that the K upon Q, which is the most important parameter for either body, has changed from what it is now, and in addition could change during the evolution if through, for example, a large change in eccentricity or whatever, there's a large amount of heating in the moon. I think the right way to pose the question is, does it matter?
Oh, it matters a lot, and that's like kind of the difference between the original election. So the model that was used for the original election paper actually wasn't aiming for the very early moon. So the phase space that we were exploring might not have been the best part, because we assumed the moon was more or less rigid, which it's not at all. So further work by Jack probably found the more interesting part of the phase space. But I think, moon started out as molten. So log numbers were higher early on. That is hard to argue against. As for the Qs, we don't know. Goldrake says they're 100. I don't think they were much larger than 1,000 or smaller than 10 or something. Now, later on, where the really interesting time that constrains the lunar tidal evolution is the Cassini state transition. And Cassini state transition by itself assumes a rigid moon with the present shape. That's just comes from the location of it is determined by the shape of the moon, and the shape of the moon seems to be fossil. And Ian has done lots of work on that, and generally it's fossil from the era before the Cassini state transition. So you can consider, my best guess would be, you can consider the moon to be rigid and have a K2 that's similar to today's during Cassini state transition. So those are the two regimes that early on, I think, pretty dissipative moon is a good guess, and at least deformable moon. And later, Cassini state transition, which is particularly important step, probably it's good to assume the moon with present-like parameters.
Yeah. In the case of the giant planets, which normally you would not think is relevant, but might be if you're talking about a magma ocean, a lot of people have thought about the dynamics of the system. That is to say, when one talks about K upon Q, you actually have to think about the specific processes like inertial oscillations or whatever is going on, as in the work of Ogilvy and Lin, or the work of Jim Fuller, where you're surfing on a resonance. Do you think any of those dynamic complications are important for the moon?
That would be probably more for Earth itself when very early on. Maybe in the first million years, who knows? But even the Cassini state, sorry, the Laplace plane transition, if it happens at something like 15 to 20 Earth radii, we might be already out of that. So we are operating completely outside of data in that case. So I cannot say that it wasn't there, but there's no reason to think that there was something like that. It's complicated enough without it.
Actually, it's the first time I hear you ranting like that. So it's an interesting perspective. But I must say, I find it ahistorical for somebody who wants to speak about historical accidents. Because in a historical context, basically you're evolving the science based on what existed before. You don't have the hindsight of, I don't know, 12 or 15 years after, I don't know, the paper in the 90s, or we don't have the hindsight of 30 years after the paper of Goldreich in the 60s. So when you're trying to explore a phenomenon, you want to complexify it to a minimum amount that introduces innovations. You're not trying to solve the full complexity. And it's not surprising that complexity accretes with time. So that's one comment. The other comment is that, and it probably builds on what David was saying, in the sense that if you want to really allow for these tides, then the physical complexity amplifies dramatically. In a sense, how physical do you want to get in describing this phenomena, and how conservative or how excessive you are in allowing for them in any given model. That's the first thing. The other thing is that if you want to handle spin orbit dynamics carefully for a triaxial and deformable body, which is what's likely the moon is in, and we certainly considered such possibilities, things get complicated very quickly. So how confident you are that you're actually describing the physics that you claim you want to describe carefully and accurately?
Well, I'll answer the last first. How sure I am that this is the right answer? Not at all. How sure I am that these factors are important? I'm completely sure right now that. Well, I'm not trying to sell here a weak history that, in hindsight that, oh, well, obviously, because I was one of the people who were not getting it until Irina Chen published her abstract. So, and I've read all these papers. I assumed that liquidity tides are not important because they were around for a while and nobody thought they were important for orbital evolution. So it's not to impinge on, say, Stan Peele, because now in hindsight, yes, it's clear where the energy has to come from somewhere for the tidal heating due to liquidity tides. But what I'm saying is given that people did independently, more or less independently, discover it in Triton, like Phil Nicholson and his group, including Chris Chai by the time. It just makes me think that have people talk to each other at some point, it might have turned out very differently. So it's not to say that we are smarter than people back then. Actually, I would not be able ever to do Goldreich 66 paper. I mean, it's just no. But there is the field has a certain conservatism, and I think since we are theorists here, we understand where things come from. But I think wider field doesn't always understand that there is people say, well, we want to stay as close to the classic giant impact. Well, there is really no reason once you realize that it was missing something to stick to it as some gold standard, just because it came first. Oh, sorry. Actually, come back. Yeah.
Well, I'm going to give 2 hours of lecture on my response to this.
So maybe brief now.
I'm not going to spill the beans right now. But to what extent have you explored other parameters?
Sorry?
To what extent have you explored in that simulation other Qs of the Earth or Qs of the Moon?
Oh, factors of two here and there. Like what I explored was what's in the paper. So
Q of the Moon in your simulations was 1 or 2, I think.
No, the Q is, I think about 50 or 100, depending on the simulation.
You had
No, K2 was what?
K2 over Q was around 100, and K2
Yeah.
is 0.025, so that means the Q of the moon was around 100.
No. This is for the Q over K2 was that for the Laplace plane transition. When I went to the Cassini state,
Yeah, then you chose a higher Q.
yeah, it was present
Just wondering
day,
to what extent you explored other Qs, that's all.
not much. Morby?
Last one. Of course, we don't know what to use.
Yeah, so the evolution you described is certainly possible, plausible, and as everybody says, I mean, not certain because nobody knows what were the parameters. I just wanted by completion mention that it might be possible to excite the lunar inclination late after the Cassini state transition, if there are still bodies, relatively massive bodies in the inner solar system not yet removed through close encounters. This is what I explored with Kaveh Palevan a few years ago, which again might be an explanation or might not be an explanation because we don't know how many bodies and what masses they had at the time. But so it may not be absolutely necessary to have a huge inclination just after the moon forming event. It's a possibility, I acknowledge fully that your evolution works very nicely, but maybe there are also alternative explanations.
Yeah, I could talk about it for 1 hour, so better not. So maybe I better move on.
Yes, let's move on.
Yeah. Okay, so this is my latest paper where we do all this and then we throw in lunar core. Okay, so it's excellent that Ian gave his talk already, so I can talk about dynamics of the body with the core. And so the idea is that you have an outer layer which is solid on short time scales. So really, for Earth is not really solid because the shape of the Earth is driven by rotation, but when we do core mantle dynamics, we assume that the hole in the mantle is more or less solid and the core is completely liquid. So when we have this case of a liquid core, I'll ignore the inner core of the moon in the whole story. There are several regimes you can have in dynamics of these of bodies. So what happens if the rotation of the fluid gets misaligned with the rotation of the mantle? Now, mantle is going to precess because it's being tugged by outside torques, and the core will want to continue rotating around the same axis before because of inertia, and then there will be a torque from the mantle on the core because the core is not taking up the same space it was before, and the hole is, in case of Earth, is considered usually to be just flattened, symmetrical hole, and in the case of the moon, it's actually triaxial. So the core is going to wobble relative to the mantle. So depending on how elliptical the core mantle boundary is, this wobble, the rotation of the core, can be very fast relative to precession or very slow. So in case of Earth, precession of the mantle is 26,000 years due to lunisolar torques. On the wobble of the core, the free core nutation around the mantle is about 400 days. So the core is rapidly nutating around the mantle spin axis, and the core basically stays dynamically coupled to the mantle in case of Earth. The moon is very different. The precession period of the lunar mantle is 19 years, which is because it's in Cassini state. So this is the same as the precession period of the line nodes. But the core notation period is much longer. It's longer than 100 years. The reason for that is just that the rotation of the moon is so much slower, and the core notation period is proportional to the rotation period and then something else. And while the precession of the lunar spin axis is really fast. So they are decoupled. And this is something that Jack has worked on. This is a paper by Jenny Meyer from 2011, where they plotted the two timescales, the two periods actually here. So the A, the curve is the period, the peaked curve is the period of the precession of lunar orbit, and which through the Cassini state also means the spin axis. So it gets longer until 20-ish Earth radii. This is Laplace plane transition, because here the precession is due to the equatorial bulge of the Earth, and as you move away from Earth, the period gets longer. Then it gets to the Laplace plane transition, and here precession is due to the solar torques, and the precession speeds up as the moon is further away from Earth and the solar torques are relatively stronger. And while the nutation period of the core gets longer, I'll ignore B here. C is the one you might want to worry about, and might have discontinuities because of Cassini state transition, which is here. But generally, the two cross before the Cassini state transition, which means that the mantle, the core cannot follow the mantle starting from a point before Cassini state transition. So for much of the lunar history, this first part happened very quickly, and then it slows down as we move out. For much of the lunar history, the free core nutation was too slow to follow the mantle, and the core and mantle are decoupled from each other. So it's very different from Earth. So why do we care? So we care because of magnetic fields. So this is another remote sensing plot of lunar magnetization. This is from Vizorek. There seems to be no problem converting these to nanoteslas in this paper. I know devil is in the details. So you got also lab samples that Ian has been talking about. So one of the motivations for looking at the dynamics of the lunar core is this mechanically stirred dynamo that could be a solution to the past magnetic field of the moon. This is a plot from Dwyer et al. 2011. Et al. Includes Dave Stevenson. And the idea is that during Cassini state transition, there might have been a large misalignment. Well, now the misalignment is small, but in the past there was larger misalignment between the core and the mantle because of obliquity of the mantle, and there might have been mechanical stirring at the core mantle boundary. And you can get a magnetic field from that. Yeah, so this is from Weiss and Tiku review paper, and this is the same, more or less the same data Ian showed. And the idea is that, well, everything is up there, but the precession is one of the candidates for generating magnetic field. And I think they put it too late here. Cassini state transition should happen earlier, in my opinion. So my idea is you just model this numerically. And when you do these numerical simulations, first thing you look up Tuma and Wisdom papers, because that's what you do. At least what I do. And it was a beautiful paper in 2001 by Tuma and Wisdom about integrations of planet with a core, like the deep Poisson integrations of planet with a core. And we implemented this in our integrator. Since this is a triaxial body, there is no nice way to integrate rotation of the moon with the core. So what we do are short period integrations where we let the moon settle in a stable state, in a local equilibrium, as opposed to the continuous tidal evolution simulations from close to Earth to further out. So we are checking up on our tidal evolution simulations by putting the moon at different places and seeing how the situation without the core compares to the situation with the core. So this is the present day moon. We put the moon we put the mantle and the core in like spinning parallel to each other. You can't even see that. The core drops right to the ecliptic in no time, while over time the mantle is blue. The mantle librations shrink over time, and the core librations shrink. Core settles spinning around the axis that's only 0.1 degrees from the ecliptic, while mantle has the obliquity of 1.6 degrees from the ecliptic, the Cassini state 2. The gray, which is right under the blue, which kind of shrinks slower, is the rigid moon. So basically, mantle spins more or less the same way a moon without the core would, while the core is doing something completely different. And the damping of librations in the mantle with a core is much faster than without a core. So core-mantle boundary right now produces more damping than the tides themselves. And you can see that the core spin period is slightly longer than that of the mantle. Because they are misaligned, mantle is synchronous, but core is driven by the friction of the core-mantle boundary. If they are slightly misaligned, then they will not be synchronized. So this is what you get for, if you just look at a few precession periods, that the core and the mantle are the opposite sides of the ecliptic normal as they precess around. So this is kind of what it looks like in terms of, so the ecliptic normal, so orbit normal is on this side, mantle spin axis is on the opposite side of the ecliptic normal, that's Cassini state 2. So this is 1.6 degrees from the ecliptic normal to the orbit normal is more like 5 degrees. And the core spin axis is on the opposite side of the ecliptic normal from mantle spin axis. And this angle is only 0.1 degrees. So the core spin axis stays very close to the ecliptic normal, much closer than the spin axis of the mantle. And these are more or less in the same plane, all of these. They're slightly out of plane because of dissipation, which induces offsets. But so we ran this much closer to Earth, and we managed to get both coupling and decoupling. So this is barely decoupled mantle. You can see there is a huge lag here. They're not at all opposite, exactly out of phase, because they're barely decoupled. This is at 18 Earth radii, but if we move to 15 Earth radii, we can have them coupled. At this point, the precession of the core is fast enough. The notation of the core is fast enough to keep up with the mantle. So first they try decoupling, but then it gets back into coupling here, depending on the initial conditions. And you can see they're in phase. So we reproduce the idea of coupling and decoupling based on the notation period versus the precession period of the moon. We find it's a little bit earlier than Meyer and Wisdom found, but it's about the same overall. So what we did, as I said, is that we tried testing this tidal evolution I showed you before. It was done without a core by checking every Earth radii and running a simulation with a core to see what the obliquity and spin rate should be in equilibrium. So we tried to be on top of, with the blue points, we tried to be the top of the red simulation. So these are our solutions for the obliquity, and this is for the spin rate. The black line is the analytical Cassini state and the synchronous rotation. So you can see, even without the core, there is a time where moon was not in synchronous rotation, where the red doesn't follow black. It's complicated why that is. There is a resonance here in the red. But this non-synchronous rotation is restricted close to the Cassini state transition. This is the classical Cassini state transition, the vertical black line. And you can see here with the spin rate, the black is asynchronous and red does not follow black for a while. This is non-synchronous patch. That happens because the equilibrium Cassini state obliquity is too high to be stable. But then when we put the core in, those are the blue points, only this one, the square frame points are the only ones where the moon is synchronous. In between, it's completely, it's slightly off synchronous because of the core. And what happens is that under this high obliquity, synchronous rotation is already very weak, because when we think of synchronous rotation, we think of the planet hovering over the equatorial point on the equator of the planet, of the moon all the time. But if you have obliquity of 70 degrees or something, you don't, the planet moves up 70 degrees above the equator or 70 degrees down. So the the stability of synchronous rotation is much weaker, and then you throw in the core, which is highly subsynchronous, and then tries to slow down the planet, it can move the equilibrium rotation out of synchronous. So this is what I'm talking about. As the moon and the as the mantle and the core are decoupled, so this is both their obliquities plotted relative to the ecliptic. The black is the simulation from 2016 paper. Blue is the mantle, red is the core. So you can see the mantle more or less follows the solid moon, but at some point it has higher obliquity to ecliptic, at some points it has a lower obliquity to ecliptic. And it's more subsynchronous typically than the solid moon would be because the core pulls it that way. The core has much smaller obliquity. Now it's only 0.1 degrees. In the past it was many degrees, but still much smaller than the mantle. And so the purple line is the spin rate of the core derived from the mantle by like just assuming that the spin rate of the core is the angle between them times the cosine, the spin rate of the mantle times the cosine of the angle between them. And you can see it follows very well. So basically the core spins at the rate determined by the friction of the core mantle boundary, but also torques on the mantle to be subsynchronous. And when it's far from Cassini state transition, it can still be synchronous, but during Cassini state transition, it's particularly vulnerable to extra torques to destabilize the synchronous rotation. So finally, this is kind of the quantities that are useful for figuring out the possible dynamical stirring and the magnetic effects. So on top is the obliquity of the core. So this is to the ecliptic, what I plotted before, and this is to the mantle. So depending on the distance, so I have here did simulations from 25 to 50 Earth radii, and then this is just analytical approximation beyond that. And you can see eventually the two converge. There are a couple of resonances along the way, but eventually the moon gets back into synchronous, as it should. But because analytical approximation assumes Cassini state. But at Cassini state transition, you have angles going up to 60-something degrees between core and the mantle. They're hugely out of sync. And if you look at how subsynchronous, the core is, there's a difference between a spin, like it's on the order of 1 at this point, because they're spinning around the axis that are 60 degrees from each other. So the two spin rates have nothing to do with each other, really. And then as we get to the present state, the difference between the spin rate of the core and the mantle becomes very small. So this is brute force dynamics applied to this problem, and it makes sense based on the previous analytical results and so on. But that was in the details. The important thing is I used the present rate of spin orbit, of core mantle friction throughout the history, which is quite strong. So it's one thing that probably changed over time, and we don't know how it changed. Okay, so this is the end of the second part. So the core of the moon is very different from core of Earth by being decoupled. And during Cassini state transition, it should have had a huge core mantle tilt, which obviously has implications for lunar dynamo, which we haven't looked into at all. Interesting consequence, which I don't know what to make of, is that if the lunar magnetic field is tied to the core, and the core had such a huge tilt to the mantle, the magnetic field was just sweeping all over the surface. You could not have magnetic pole as we have it on Earth. So some people claim they can find paleopoles, some people claim they can't. So I'll just throw that out there and let people discuss it. Thank you.
I have a question. How does the angle you're getting there compare with the assumptions in Dwyer et al.? The core mantle tilt angle?
I haven't really looked much into it.
Okay.
I think there was I couldn't figure out because Dwyer used some kind of complex polynomial, which I wasn't sure where it came from. Now, the obvious difference is that if you assume classic tidal evolution, which had smaller inclinations, you get smaller obliquities. You still get very large obliquities, but not as large as what I get. But then, it's if you get later excitation of inclination that Morby talked about, you might not get very high obliquities still. Like if you get past Cassini state transition and then you incite inclination. That's kind of that's the biggest caveat probably, because that's the alternate history which is viable.
Oh, this is extremely interesting to me, because Wieczorek and Four concluded by looking at the density of craters on the moon that during the heavy bombardment 4 billion years or so, the moon was not synchronous because they don't see any asymmetry between the leading side and the trailing side of the moon. And they proposed at the time that the biggest impacts, the basin forming impacts, drive the moon out of synchronous state temporarily. But actually, from your plots, 4 billion years ago, the moon distance was at 36 lunar radii, and at 36 lunar radii, you don't have a synchronous rotation. So that would be a fantastic explanation of the uniform crater density.
I would love to agree with you, but the thing is, because Wieczorek and Four, like the statistics were somewhat borderline, like they were not super strong. So all you need is to flip the moon a couple of times, like the leading and trailing in impacts, and that would erase the preference. So you don't really need long-term non-synchronous rotation. So I mean, yeah, I don't think that's a strong argument for having non-synchronous rotation.
What are you thinking is the overall radius at the time of the latest bombardment? This was the question of converting these.
In his plot, it's 36 lunar radii. If you go back to your slide where you have the migration.
Did I have one?
Yes, before this, just before that. Here you go. 4 billion years before present, it's 36, 37 lunar radius, terrestrial radio. So I don't know it by myself. That's what he says. So at that distance in his model, the moon is not synchronous.
Yeah, well, I don't. Let's see. It's possible.
I mean, we don't actually know.
Yeah, we don't.
Yeah, okay.
This is reasonable. This is reasonable. Yeah, but lake bombardment is not what it used to be. So maybe many of those craters formed somewhat earlier. In which case, yeah.
Craters you see because there is saturation before. It's stable at 3.9, 4.1, 4.2.
Yeah, well, that's.
So it could be there, but
Yeah, like 40 is what we care about most, I would say, reasonably. But, we don't know. 40 Earth radii, sorry, that's, yeah.
Okay, so you're using these Poincaré-Huff models to describe core-mantle interaction. And, they're really describing a mode of oscillation or mode of fluid behavior in which the velocity field is linear in the positions. Now, once you start exciting these high misalignments between core and mantle, I think you'd really have to worry about significant instabilities, particularly boundary layer instabilities that would disrupt the global flow within the core. And then the models, I think, will lose applicability, and you may have to start worrying about some of the conclusions.
I think it's very fair to say, that, the extreme nature of the evolution. So the extreme obliquities you get are we can see they're not a mystery. They come out from all the other parameters. Like, because we have Cassini state transition, we might have had large inclination. Even if we didn't have large inclination, you have large obliquities. So all these things should be there. Now, I was thinking for a while, like, how should the core behave? So, for example, for a while, I thought putting on stronger and stronger dissipation, maybe that would just couple the two, and you would not have any of large. But what happened eventually is that the moon decided to just stop spinning altogether. That was energetically the best thing to do, because they could not move together, so they decided just not to move. So I haven't seen anything that looks unphysical, but given, yeah, nothing is small in this, no inclinations, so.
A comment about coupling. This is not a simple problem. I know because I once argued with Stan Field, who is no longer alive, sadly, on exactly how to do this right. And as you probably know, he played this game in trying to understand how to get into the 3-to-2 resonance for Mercury and so on and so forth. And these things had to do, in part, with what you were talking about viscosity, and I think we have consensus there that it's a low viscosity. But then there's the question of what's actually happening in the Cold-Matter boundary. And he liked the idea of spherical Cold-Matter boundaries, in which case the drag coefficient is just some very small fraction of rho v squared, which is actually what we did here. And it may not be right. We don't actually know, because there can be topography and there can be a lateness. In the case of the moon, it's small, but it might even matter. So I'm not really bringing up a question. I'm just reminding everybody that there are aspects of this whole story that we don't fully understand.
Yeah, I could not really model this as a spherical spin core mental boundary. I went for triaxial, so it would have been much easier if it was spherical.
I've never understood why Stan wanted spherical.
You're right. I actually, in the case of, I mean, maybe I'm sitting on the fence, but I argued with Stan that he should not be thinking of the Cold-Matter boundary of Mercury as a sphere. And if you look at his classic work, which is frequently cited, whereby you use precession and the other, libration, sorry, the other measurements to get the size of the panel and so forth for Mercury, you look carefully at it, he's assuming that the Cold-Matter boundary is a sphere. And I don't think he should have done that. If I'm right, then I should also be worried about the moon.
Yeah, well, this should be done more times.
I think the Mercury problem actually deserves more attention. And maybe with every Colombo we will get it.
Okay.
Anyone else? All right, thank you much one more time. All right, next. Yes. Okay, so next up is Jack, continuing his lecture series here. Briefly introduce him again, his background, expert in planetary dynamics, did some early work on chaos in the solar system and the stability of the solar system, and has published a number of papers on the evolution of the moon's orbit and the dynamics of the lunar core. So yeah, I will let Jack take it away.
So I guess I have to speak over here. The next two lectures are simply response to Mathieu's work, basically. So there you go. This one is about the first half of his 30-minute talk. And then the next lecture is about the second half of his 30 minutes. So this is our investigation of the early evolution of the Earth-Moon system with a fast-spinning Earth. And this lecture was made without regard to what other people might present, so it has some redundancy. So here's a giant impact scenario. You've all heard about this. I'll just proceed. My talk won't be very long if I skip all the slides. So most of the.
It would be useful to go over it again.
Over it again. All right. The giant impact scenario by Hartman, Davis, Cameron, and Ward, and impacts are likely. They can account for the Earth-Moon angular momentum, which was a good thing at the time. And then they're consistent with low iron abundance relative to the Earth. And that was some of the main reasons for going with the giant impact scenario. And, but the problem came, maybe it happened earlier, but at least this figure comes from Canup 2008 that shows that the material that makes the moon is primarily from the impactor. If you get enough material in orbit to make the moon, then it comes primarily from the impactor. So that's a problem when you look at isotopes. And this is the line on which terrestrial rocks form in two different oxygen isotopes. And these are the lunar rocks. They fall on the terrestrial fractionation line. And then other things like HED meteorites in Mars fall on different lines. So there's a problem with isotopes. And then more generally, chromium isotopes, oxygen isotopes, tungsten isotopes, and titanium isotopes all agree with the Earth and the Moon. So that is a problem with the original giant impact scenario. And then I stuck this slide in because it just kind of stirs the pot a little bit. There's a recent measurement of vanadium isotopes. And vanadium isotopes, there's the Moon significantly different from the Earth. And so the question is, how do you explain that with any of these high impact scenarios? The vanadium isotopes agree with chondrites, all different types of chondrites. So this supports this idea that the Moon was formed by an instantite chondrite. But I don't know enough about isotopes to challenge this plot. But, I thought I'd throw it in. Other possible resolutions of this isotope problem are equilibration isotopes a la Stevenson and other people. Yes, anyway, or the impactor similar to the Earth, or a hard impact and resonant despinning, which is what I'm talking about this time, and then hard impact with high obliquity, which is discussed in the next talk. Both of these are due to Chuk and collaborators. So the idea of Mattia and Serra is from 2012 is that the hard impact excavates terrestrial material to form the Moon, and also Canup had a similar model. But the problem is that the Earth-Moon system is left with too much angular momentum, and then they evoke a capture into an evection resonance, which drains the angular momentum, and then you find that the system is left with the correct angular momentum. So here's the more details of their scenario, which Mattia just showed. So there's, this is the semi-major axis. The major axis of the Earth moves outwards until it hits the evection resonance. The evection resonance is further out because of the fast spinning Earth. The J2 is higher, so you have to go further out before this precession of the pericenter can match 1 year, which is the period of the motion of the Earth around the Sun. And so the evection resonance happens further out in the Chuk scenario, which is a virtue. And so it hits the evection resonance. When it hits the evection resonance, the eccentricity skyrockets. In their calculations, it gets to 0.5 or 0.6. It's captured in the evection resonance by a balance between the eccentricity dampening due to dissipation in the Moon and rise of eccentricity due to the passage in the evection. And then while you're in this equilibrium state, the Sun drains the angular momentum and the semi-major axis drops until you get to a point where the motion at the pericenter of the Moon matches the Earth rotation, then you fall out of the evection resonance. And then, so that's the basic scenario. And then this is a plot of their resonant angle, which is twice what I would call the resonant angle. So they get a libration around 180 degrees, whereas the evection angle of the pericenter minus the longitude of the Earth is either plus or minus pi over 2. So anyway, it's just a difference of way of plotting. So this is the Chuk and Stewart model. They use our orbital integrator, and they use Jihad's Lee-Poisson method for Earth rotation. They didn't include the Moon, I believe, rotation, but they included dissipation in the Moon. And then they had an ad hoc model of tides, which I disagree with. So let's see, here are their results. So this is the initial angular momentum measured in these units. And in these units, the final angular momentum of the Earth-Moon system is around 0.35. That's the target. And so they start here, and then they go through this evection process, and they end up with this final value. So you find for particular values of this dissipation parameter, you find the angular momentum of the Earth-Moon system is recovered. The A parameter is a measure of the relative dissipation in the Moon to the Earth. So a high dissipation in the Moon, that's small q Moon, means a high A, and low A means low dissipation in the Moon relative to the Earth. So there's a particular narrow band of A parameters where you get the angular momentum of the Earth-Moon system. Now, some people argue that there's a philosophy issue, that because you require a particular range of parameters, that this is you should argue against this scenario because it's unlikely. Why should the parameters be just right to form the Moon? But I object to that because there's only one Moon. We don't have statistics about other moons, and so why shouldn't the Moon have that particular value of the parameter? But there's another reason later I'm going to show you why the narrow range of parameters is bad for the Moon, not for me. So here's the Chuk tidal model is not the Mignard model and not the constant Q model. So they take the torque on the Earth as proportional to the angular momentum of the Earth, I believe. This is generally not true of any real tidal model. And then there's an ad hoc factor of S, which is introduced, I don't remember why. The acceleration on the Moon was presumed perpendicular to the radius, and you saw in the Mignard tidal torque that that's not generally the case for a tidal model. And then the acceleration of the Moon due to satellite tides is purely radial, and the purpose of this is to damp the eccentricity. But this is also not generally true of tidal models. So we thought we should redo this with tidal models that we believe. So we did this with well, here's the Mignard model, the constant delta T model, which we don't use, but here are the formulas, and you see that none of those assumptions are valid in the Mignard model. So we made a new model for the evolution of the Earth-Moon system in order to test the Chuk scenario. And we, of course, used the Wisdom-Holman method for evolving orbits. Everyone does. And then the Tuma-Wisdom model for Earth rotation and the Moon as rigid bodies. We are only including Earth, Moon, and Sun, but the program includes the possibility of including all the planets if we thought that was relevant. We include Darwin-Cole constant Q tides. That's based on this plot I showed yesterday of what's experimentally known about the Q of the Moon. It's consistent with a constant Q. And then we include, in this model, we're only including tides on the Earth due to the Moon, and on the Moon due to the Earth. We didn't include the solar tides or the cross tides. And then we also include intrinsic wobble damping with a rate given by Peel in '73, and I did a completely independent calculation of the wobble damping rate in 2016, and I found my estimate agrees with Peel's rate. The rate used by Mattia is about a factor of 7 smaller. So that could be a factor in the differences of the results for the Moon.
There was no rotation of the Moon.
This is, yes, we include rotation of the Moon.
No, but sorry. My paper did not have the.
Oh, I'm sorry. It's your later paper I'm thinking about. Yeah, I'm sorry. I'm confusing all the. So because we don't have many results to compare to test our results, it's nice to have different tidal models and see that we always get the same result, and we will eventually do that. But right now we have this one model. But in order to check our results, this is done with Zhen Yang Tian. We each independently wrote our code and compared the results, and we found that we agreed. So that's some evidence that the code is correct. We also, because we have various wobble instabilities, we were wondering whether the Lee-Poisson method was a valid way of integrating triaxial bodies. And so we programmed a quaternion evolution code for the rigid bodies and tested that and found that the Lee-Poisson method worked fine. And so, so all subsequent results after that test used the Lee-Poisson method. So this is kind of an intermediate state of evolution. So here's our results. The eccentricity of the lunar orbit in our result, using similar parameters to what Mathieu used, only reaches an eccentricity of 0.35. They reached 0.5 or 0.6, so we reach a smaller eccentricity. Otherwise, the evolution is, it goes through all the same phases. The resonance argument oscillates around pi/2, and then which is the evection resonance. And then what we found was that a constant Q model, our constant Q model, extracts too much angular momentum from the Earth-Moon system. This is the Mathieu result, and this is Mathieu-Chuk result, Mathieu-Stewart result, Chuk and Stewart result. Sorry, I'll get it right. And this is Tian wisdom. And we extract too much angular momentum, but that shouldn't be taken too seriously because it's just a particular tidal model. Maybe different tidal models could give different results. Then we added, our model is completely general, so we added inclinations and obliquities. And so if you add a 10-degree obliquity of the Earth and some mutual obliquity, this is the obliquity, I've forgotten what that obliquity is. It says epsilon, but I'm not sure that's epsilon. You find a smaller, even smaller range of where the angular momentum is withdrawn. That's the triangles. If you enhance the wobble damping even above the Peel wobble damping rate, you can broaden that range. And so, so again, it's roughly consistent, even with inclinations to the Chuk and Stewart result. This is hydrostatic, yeah. In these calculations, we chose it to be the hydrostatic shape at 5 Earth radii. So we didn't let it change. Yeah. So the summary here is that the angular momentum is still reduced in a narrow range of the A parameter. We withdraw too much angular momentum, but that could be a consequence of the tidal model. What we note is that in both of these models, large eccentricities result. The tidal heating formula is proportional to the square of the eccentricities. It's proportional to the inverse 6th power of the radius. So we're close in and we're at high eccentricity. So the moon is going to be strongly tidally heated. And so, so we'll deal with that in the second part. But I guess first there's this, we explored a wider range of Q, Earth, and A parameter, and we found a new way of extracting angular momentum, which we call the limit cycle. And so this is a plot for a larger value of A parameter and a larger value of the Q of the Earth. And now the evection resonance angle doesn't oscillate about pi/2 or minus pi/2, but it circulates in a non-uniform way. It has concentrations. And so it's affected by the evection resonance, but it's not in the evection resonance. And so if you plot in the phase plane, eccentricity cosine evection argument versus eccentricity sine of the resonant argument, you find that the system has evolved into a cycle. And so this is a cycle that the system is attracted to, so we called it a limit cycle, naturally. And so, so this is the dynamical configuration that the moon finds itself in. And then this is what happens to the eccentricity in the limit cycle. It now, instead of going to 0.3 to 0.5 in eccentricity, it only goes to 0.1, and it oscillates between 0 and 0.1. So an advantage of this is the tidal heating is going to be smaller. And then if you look at a larger plot, you find that here's the earlier result of being in the evection resonance, and in the limit cycle, you also get extract angular momentum, but over a larger range of the A parameter. And this range we'll show later depends upon the Q of the Earth. So here's the summary again. Evection resonance drains angular momentum in a limited range of A. The evection limit cycle extends the range of A to a larger value, larger range.
What is the lunar obliquity doing in this phase of evolution, your calculation?
don't remember. I'm sorry. We'll show plots of lunar obliquity later in the talk tomorrow. So the tidal heating formula, again, depends upon K2 over Q of the moon, mass of the Earth squared, inverse semi-major axis to the 6, eccentricity of the moon squared. If you take this formula seriously, then these evolutions to large eccentricity and the evection resonance would imply very large tidal heating. An order of magnitude calculation, assuming there's no thermal evolution of the moon, says the moon should the temperature of the moon would rise by 10,000 degrees, which is absurd. So clearly the structure of the moon has to change as a consequence of the tidal heating. So that led to a coupled orbital thermal model because of the large tidal heating. And so this is, this is, here it is. So it's done again with Shen Liang Tian and me and Lindy Elkins-Tanton. And Lindy basically is responsible for doing the thermal model of the moon, and Shen Liang and I are responsible for the orbital model. And I actually programmed the thermal model, but it was developed by Lindy. So, we're coupling those together. I just mentioned one thing, that this is just a power series, the first term in a power series for the tidal heating. There's the next term for a constant delta T model is 18e to the 4th. And so at high eccentricity, you could get much more tidal heating than is predicted by this formula. You should remember that this is only the first term in a series for any tidal model. So again, we're going to have K2 over Q of the moon change, which is going to change the A parameter and affect the orbital evolution. So we have orbital evolution affects heating, that affects K2 over Q affects A, which that feeds back on the orbital evolution. So it cycles through. So the assumed physical model of the moon is all from Lindy, and I'm sorry, I can't defend it. I hate this. But I can't defend it. So here it is. So the moon forms rapidly, solidifies rapidly following formation. In only 1,000 or 2,000 years, it's 80% solid. That's because it has a free surface and radiates energy efficiently. And then after a couple thousand years, the plagioclase lid starts to form, and then that drastically slows down the cooling. And then it takes on the order of 100 million years for the residual magma ocean to solidify. And then the magma ocean is of undetermined width, depth. It could be 1,000 kilometers, 100 kilometers to 1,000 kilometers. I think we used 100 to 200. And then the time to reach the evection depends upon the Q of the Earth, of course. For the Q of the Earth of 100, this is 10,000 years. And remember, it takes only 1,000 years to put the moon into this configuration. And for a Q Earth of 1,000, which Zhangli likes, this would be 100,000 years. So it's basically plenty of time to form this state of the moon that we assume. We assume the thermal model as developed by Lindy, which heat transport is in the lid is by conduction, melt migration. The magma ocean is assumed to be adiabatic with conducting with an adiabatic temperature profile, which is very steep in the moon, so it's characterized by a single temperature. And then heat is conducted out of the magma ocean through the lid, and then there's latent heat and radiogenic heating included in the model. And I can't defend it. I'm sure Dave wants to challenge me. But anyway, so we calculate tidal heating in the lid using the Peel and Casson formula, the two-layer model developed by Peel and Casson, and maybe Peel, Casson, Reynolds. So that gives you the K2 as a function of the thickness of the lid. And then the material Q is related to the, by Ojikangas and Stevenson formula, it depends strongly on temperature. And then the lunar Q is related to the material Q by averaging. And then we do the same rotational orbital model as we had before. So I'm not going to show you the evection results, but I'm going to show you what happens in the limit cycle. So in the limit cycle, this is eccentricity as before versus time. And now it's showing in blue the A parameter as it evolves. And you can see the A parameter evolves from maybe 14 to 17. It doesn't evolve very far. So the fact that the range of limit cycle has a big range of A parameter comes in handy here because it doesn't go out of the limit cycle as the tidal heating changes the A parameter. In the case of the evection resonance, the A parameter changes markedly by a larger amount. And so the narrow range of A parameters that allow stability of the evection resonance make the evection resonance unstable. So here are the results of the final angular momentum. So the red ones are the simulations without the coupled model, and the black ones are with the coupled model. And you can see that the without coupling to the thermal model of the moon, you have withdrawal of angular momentum from the evection resonance, but with the coupled model you don't. That's because the A parameter varies a lot because of the strong tidal heating. But in the limit cycle, you get almost the same result when you couple to the moon. And so the limit cycle is an alternate way of explaining the angular momentum of the moon. It's a little bit too high, but remember we haven't included tides from the sun, which withdraw angular momentum. And we also haven't studied a wide range of parameters. So here's one study of parameters. This is for different hues of the Earth. This is the curve you get, and each one is displaced. So this is the angular momentum of the Earth-Moon system after displacement, and this is what you get in the limit cycle. And so basically, the only main result is as you increase the Q of the Earth, which again, people like Zonley argue that it should be higher than 100, you get a wider range of stability of the evection limit cycle, and the angular momentum is closer in alignment with the Earth-Moon angular momentum. This is the summary. I don't know if you need to know. I don't know if I need to read this. The evection resonance can drain angular momentum over a narrow range of A parameter. Our model, which we consider a more genuine tidal model, genuine constant Q model, it reproduces that result. Modest inclination and obliquity decrease the range of A that work. The evection limit cycle can withdraw angular momentum over a larger range of A parameter. Tidal heating is large in the evection resonance, so the moon parameter's thermal state must be taken into account. We made a model to do that, and the evection resonance no longer drains angular momentum, but the limit cycle does. And there you go. I just mentioned that even though we didn't study this limit cycle with the other tidal models, Robin Knupp has studied the limit cycle with the Mignard model, the constant delta T model, and she finds results that agree with ours, although we haven't done a detailed calculation because her paper is not available. But anyway, she basically finds the limit cycle as well in an alternate tidal model. So, but the detailed estimates of angular momentum withdrawal are not available, and she doesn't do a coupled model, as far as I know. So that's this talk. I don't know how long that was. How long was that? So that was, I'm 30 minutes ahead. I could give my second talk now if you want. No. Because it follows right after Machia's talk, so it would be appropriate. But I won't. I'll wait till tomorrow.
You should give us time for things to sync properly.
Okay. So any questions or comments about this work?
Just a question of clarification, probably not distracted, but what sets the system in the actual resonance versus the limit cycle?
What is what?
What sets the system to go into the actual resonance?
Oh, it's the capital A parameter. The larger dissipation in the moon leads to the limit cycle, and smaller dissipation in the moon leads to evection resonance. You mean what? How do we understand more detailed mechanism of going into it?
Okay, so that's the initial A.
The
A evolves.
That's the initial A. That's right. But A in the limit cycle of A doesn't vary very much. So the initial A is a fine way to parameterize it.
So if you start with a lower angular momentum, does the whole curve just shift down and you reach the Earth, or do you still?
No, the low angular momentum goes back to the previous talk. basically, the J2 of the Earth is smaller, the evection resonance occurs closer in, and then when you rise in eccentricity in the evection resonance, you almost immediately hit the instability where the motion at pericenter matches the rotation rate of the Earth, and the evection resonance is unstable. So you don't get captured for a long time in the evection resonance.
And so, okay. So what is that in terms of like units of the present day? And what's the lowest angle length you get before you hit?
We did not study this as a function of the initial, we just chose Mathieu's value for the rotation rate of the Earth. Yeah. All these things take time, and it's hard to explore all parameters, but you're all tidal models. What we'd like to do is explore other tidal models, make simple models for the evolution and all these things, but yeah.
My question is a bit hypothetical and very general, but it's something I've been thinking about. Can we, from studying the tidal evolution dynamics of not necessarily the Earth-Moon system, but any host planet and satellite, can we, at one point, from certain anomalies, maybe infer that we have a moon orbiting the primary moon? I know we haven't seen this yet, but
You're concerned about whether exoplanets have moons?
no, I'm concerned whether exomoons have moons.
Exomoons have moons. Whether moons are exoplanets can have moons, I have no idea. I'm sorry. I don't even know the answer to the first question.
Is it possible?
I think there's some detection now of an exomoon, but I don't remember details and how reliable it is.
But theoretically, is it possible to have a moon orbiting a primary moon if the first moon is big enough and far away from the host planet?
I would say in principle, yes, but I don't know the details.
Can I answer that?
Okay.
So the AUB sub-moon have to be very close to there isn't much space where you can see, so the tidal evolution will be very fast. People have actually proposed that Iapetus, a moon of Saturn, might have had a sub-moon that fell onto it. It has a equatorial ridge, so the moon had turned into a ring and it fell on it. So, and that's the best case for it, because this moon Iapetus is very far from the planet, so there's more space around it than the sun, which also wouldn't have lasted very long. So yes, they can last for a short time, but
Thank you.
Any other questions?
Oh, come on. Oh, a question. Dave, may
Don't
I?
worry about me here doing this. Do you have a question? Go.
May I comment on Dave's comment from the last talk about there's no reason to assume the core mantle boundary is spherical, as Stan did, I think. We have our paper that was quoted by Mathieu, the Meyer and Wisdom 2011 paper. We calculated the ellipticity of the core mantle boundary from the hydrostatic shape of the core mantle boundary due to the fact that the mantle is not spherical, and we deduced what the ellipticity was as a function of radius, and we compared that to the current measurements using laser ranging of the ellipticity of the moon's core mantle boundary and found close agreement. So I think there's no reason to assume spherical boundary, as Stan did.
so I have to object to the fact that your resonant angle is half of what it should be. I know it's a philosophical point, but I think you should have it.
Dynamically, it's a resonance that involves E squared cosine 2 sigma in,
Yes.
in the resonant evection. So the sigma is naturally half of what you use. And the phase space, if you look at the phase space plots, the phase space is double load when you plot it versus E cos sigma and E sine sigma. If you plotted E2 sigma, you wouldn't get this this figure. You wouldn't get
then you would get an ellipse, right?
No, but the second order, the bifurcation diagram for second order resonance is well known, and you will always get two, a lobe above and a lobe below when you, it's just the right way to plot it. I'm sorry.
Okay, well, I'm an astrophysicist. I think I'm weak in mathematics department, so I'll have to yield there.
Oh, but the bifurcation diagram is well known. You get a certain characteristic pattern of unstable and stable fixed points as you change parameters through the resonance, and you get a double lobe shape, a figure eight shape. Okay. But it doesn't matter what you plot.
Of course, but Hamiltonian term has two sigma, so there's that.
Moving away from the technicalities of angles. So this may be more of a general question for the room, but obviously for all of these, most of these calculations, you assume that the lithosphere is rigid, right, and responding elastically to the forcing. Are there tidal terms that are important that are forcing on a long enough timescale that a hot, viscous relaxation of that crust would become important? Are there any long-term tides that are important to these sort of mechanisms?
Long-term tides, longer than an orbit period.
I mean, Dave, do you have a back of the envelope calculation for a relaxation time of a hot 10, 15 kilometer lithosphere or lithosphere?
So the general answer to your question is that when, for example, you see this formula that you quoted, which might have come from Stampede, although it
Which one?
was also in Peter Goldreich's work.
The tidal heating work?
The one which says energy dissipation goes as K2 upon Q times E squared.
Yes, I'm looking for it. I forgot where it is.
I think I'm responding to your question by observing that it's there somewhere.
I know, I'll get it. Oh, it's, yeah. Okay, I'll go more slowly.
You had it at least once.
I know, it was there.
But it's important. There it is.
Yeah.
Peel and Castle, which I should remind all of you, figured very prominently in the work that most people associate with those guys, which is ILO. Because what they said, probably incorrectly, but let's not go into that, is that the love number changes. The Q might change as well, but the love number changes because it has to do with how much of the planet is liquid, how much is solid, and they assume that it started as a liquid at the center and the region got thicker, and so the love number went from an elastic value. The current moon has a very small love number. It's actually more important than Q. Think about that. The current moon has a very, very small K because it's elastic. But if you were to go all the way to a thin shell with fluid underneath, K approaches unity. So to come back to your question, the way I would answer it is the following, that when you write a formula like this, you're lumping all your ignorance into K upon Q. And I'm being serious when I say it that way, because the reality is that you should write down a model that treats the planet or moon as a body, which has a rheology that varies with position. And then you solve that horrible system, and it is horrible, to extract from it the total dissipation associated with the actual deformation. And the things that take the place of love number and Q are local variables that depend on the local properties of the rheology. So it actually matters whether you have a shell with an ocean, or whether you have a core, or whether you have a core-metal boundary, and blah, blah, blah. And you might finally be able to write it this way, but you have to remember that K upon Q should not be thought of as a property of the planet. It should be thought of as an integrated property of the materials within it. And
And so you can have a lithosphere that is, in quotation marks, rigid, and yet the love number can be large because there's an ocean underneath. So you have to think through what the actual deformation is as well as the dissipation. And in that sense, they're sort of independent issues because I can have a large love number, as for example would happen if the moon were liquid at any point, or I can have a small love number because it's behaving rigid, and I can have a large Q, which is low dissipation, as you can see from that formula, by saying that the medium is intrinsically non-dissipative, which might be true for a liquid. That's why people talk about large Qs for the giant planets. Or I can have a low Q, which is intrinsically dissipative, because when I deform the material, it starts melting. So it turns out that the range of possible K upon Qs is absolutely huge. And that's why, to give you a concrete example, Steve Squires long ago wrote a paper basically saying tidal heating at Enceladus is unimportant. And now we're talking about tidal heating on Enceladus, which is 3 or 4 orders of magnitude larger. And it's possible because not only can the Q be different than what you thought it was, but the K can be enormously different. And I've often made the case that you really have to worry about the love number because that's where a lot of the action is.
I have a slight response to that, if I may. Peel and Casson gave 2 derivations of their tidal heating formula. One derivation assumed the moon was incompressible, which they assumed, which they measured the error of that formula by to about 90% correct that it was incompressible. And if you assume the moon is incompressible, all of the details of the structure of the moon go away, and you can derive this tidal heating formula entirely in terms of H2, the displacement of the surface.
But it's not a fluid, and you get partial melting. So to me, incompressibility is irrelevant.
Well,
you can take an idealized model
for the moon
and get something simple. But my point is that they never are. They're always multi-component systems. And the kind of theorems that lead to simple results arise from assuming that the entity you're seeking to describe has simple properties, like, for example, an incompressible fluid. I really think that that's not useful. And you can come up with examples that show that it's not useful. And the way you do it is by thinking about systems where the dissipation varies hugely with space, depending on whether you're doing it in a shell or wherever. We don't, of course, know where the dissipation is occurring. That's one of the problems. So if you look at the literature on Enceladus right now, some people think the dissipation's in the shell, some people think it's in the core, there are even people who think it's in the ocean. So you can get all sorts of different results, and I don't think, I mean, of course, in the end you can write it this way, but I don't think there's a simple connection between the K upon Q and that formula and what you're saying about the material properties of the body and where the dissipation is actually taking place. And I think that actually matters.
So what level of deviation from incompressibility would you assume is correct?
Say that again?
What deviation from incompressibility would you assume all these complexities amount to?
I can't even use that language because it doesn't apply to a system that has melting and freezing. So I don't even think that language works when you have a phase transition. Most of these systems have phase transitions. A partial melt, by the way, is compressible, but it's not, you can't use one phase equations from fluid dynamics to describe how a partial melt behaves as it begins melting. The incompressibility, of course, comes about from the fact that the liquid and the solid have different densities, but they are separately incompressible. But the amount of each changes as you change temperature.
Switch kind of topic to the question of fine tuning and, why some processes give you the results that they do. So there are two cases here which are very interesting. One is the inclination of the moon one gets from the so-called eviction resonance in Two-Man Wisdom 98, and the second is the floor, what I thought was the floor of that plot for how much angular momentum you lose in the eviction resonance. Those plots of angular momentum versus in the final angular momentum versus A, which are kind of look like a hole with a flat bottom. And the bottom, in my model, the bottom was more or less where the current angular momentum is. And that bottom doesn't depend on Q's or A's or anything. It depends on the synchronous orbit, so that was one thing that looked good, that just because of where the synchronous orbit is, you end up with more or less the current angular momentum, which is also why in Two-Man Wisdom 98 you don't lose much angular momentum. You enter evacuation and then you exit right away, because that's where you are really at the very end of it. So those are now I'm inclined to think, in the absence of other evidence, that both are accidents, that that we end up with the right angular momentum in this plot, or that in Two-Man Wisdom 98 you end up with the right inclination of the moon after eviction for the canonical giant impact, for the canonical tidal evolution theory. So I don't know if you have any comments on that. Kind of.
I'm not sure I should comment instantly, but I'll try. So your tidal model has this S factor in it, which is not a part of any real tidal model. And this is probably giving rise to the fact that your angular momentum has the final value that it does. And so since I don't agree with that formula, I'm not sure I would agree with your final angular momentum being special. But I also mentioned that in the Knupp results, that she uses a constant delta T model, and she finds even lower angular momentum, final angular momentum, than we do. And so it's going to be a function of tidal model.
Yeah, well, in their case, you are actually using numerical model that's complete. Their model is analytical, so I would not treat it on the same level. I haven't seen the paper, but I wouldn't treat it on the same level.
I agree with you, actually. We did the semi-analytical model also, and we found some, I hate to admit it, disagreements with our numerical model, which were unexplained. I think I now have an explanation, but their model would suffer from the same problem our analytical model had. And so the answer is unresolved.
So on that point, is it a problem if the limit cycle or the resonance actually loses more angular momentum than you want it to? Because are there not other processes that could kick you out early? So if you had, an impact or whatever, could that just kick you out early and you just end up with a higher angular momentum than the sort of calculated bottoming out?
Sure, you can always say the thing.
I mean, that's basically my career so far, so that's good.
But the timescales are this is a million years, so maybe the moon was hit during that time. So we're not considering stochastic events. The problem is, apart from stochastic events, which Morbidelli will maybe talk about. No, you're not going to talk about that. How do you get the large angular momentum out of the system? And so if you hit it, you wouldn't get as much out as if you let it go through the whole evolution. So that would be an argument for no impacts during that time. Okay, so the next talk tomorrow is about Mathia's next thing, the high angular momentum, high obliquity scenario. And then we've applied the same Wisdom-Tian model, which applies at all eccentricities and all obliquities. It's just a matter of putting in different initial conditions, and the model already works. And then, but we didn't explore his initial values, and so we've explored those initial values, and we'll tell you about that tomorrow.
All right, that's a very nice conclusion. All right, let's thank Jack one more time. And 30-minute break, is it?
Yeah.
Okay, see you in 30 minutes.